All right, this brings us to section 2 of the book, for those of you that are keeping track of what section you're in. It's never that important to me. But those at home keeping track, section 2, chapter 12, alternating current. Once we go down this path, nothing will ever be the same. You will look back at the days when you played around with DC, and DC was your biggest challenge, because AC is going to open up a whole bunch of new problems. But AC is good stuff. AC is like what our power is. What's powering this building right now is AC. Okay, AC is what the signal from the cable company to give you pay-per-view channels is AC. You listen to the radio on the way home from school tonight, you're listening to an AC signal. So the DC world it's worse than black and white. I mean, it'd be like nothing. AC is what really makes stuff work. So after completing this chapter, you're going to be able to describe how an AC voltage is produced with an AC generator, define alternation, cycle, hertz, sine wave, period, and frequency, identify the parts of an AC generator, which ironically we already did 2 weeks ago in lecture, define peak, peak-to-peak, effective, and RMS, explain the relationship between time and frequency, identify and describe 3 basic non-sinusoidal waveforms, describe how non-sinusoidal waveforms consist of the fundamental frequency and harmonics. I like this one here. This is the kind of stuff you learn while you come to college. Understand why AC is used in today's society. You'll have that going for you. Describe how an AC distribution system works. I could do that for you right now. It works quite well, thank you. Identify and use the math associated with AC. Now, one of the big misconceptions is, and I kind of grew up hearing about Thomas Edison. Some of that may be from the fact that I'm from the Northeast. And, Thomas Edison basically was the founding father, if you will, of electrical distribution commercialization in the U.S. You go to New York, and the utility company is Consolidated Edison, Con Ed. And it got its start from a guy named Edison. He was in heavy debate with a guy, Nikola Tesla. And Nikola Tesla was the father of alternating current. And Edison wanted DC distribution. Tesla wanted AC distribution. Who won? Tesla. Edison was wrong. But yet, again, growing up, I knew the name Edison. I didn't know the name Tesla. Why is that? Why is that? I'm not a historian, but why is that? Actually, Tesla, well, truth be told, a lot of people think maybe he was not of this world, okay, because this guy had some brilliant ideas. Edison died, and they, opened up a memorial and museums and everything else. Tesla died. The FBI came in and confiscated all of his materials. And you want to know what's going on behind the walls at Area 51, behind the fences at Area 51? Probably some of Tesla's work. I mean, he was out there. The dude really was out there. Brilliant. Whether or not he was not of this earth, well, who knows. But anyway, the world adopted his electrical distribution system. Tesla said, AC is the way to go.
He wasn't American either, was he?
No. I don't know what his citizenship status. I believe he was an immigrant, and he came here for a better life and to teach us about the ways of AC. We got that going for us. He was actually, Tesla was Serbian, I believe. AC generator produces an alternating voltage using the principles of electromagnetic induction. This is a review. Blast from the past. A couple of weeks ago, we done talked about this stuff, right? Here's our magnetic field, North Pole, South Pole. We have a rotating armature. That rotating armature maintains connection through 360 degrees rotation through these slip rings. That means we harness the entire alternation of the armature through the magnetic field. So we get that 360 degree waveform out of it. And this is basically, as we rotate this armature through, we create the positive alternation, and then the negative alternation, and then we repeat the cycle. So how we rotate this, how we rotate the shaft, right? It's really up to us. It could be water from a dam, hydroelectric, it could be a wind turbine that's turning the shaft, it could be a gas turbine, it could be a steam turbine, we could be heating that water with nuclear, with coal, with diesel, however we want to do it. Bottom line is we got to get this shaft turning. Once we get the shaft turning, get the armature turning through the magnetic field, we're generating AC power. AC power. Cycle, each time the generator completes one revolution, we call that a cycle. Its output voltage is referred to as one cycle of output voltage. It produces one cycle of output current in a complete circuit. Key word is in a complete circuit. Because if you don't have anything connected up to that and that thing's just rotating through, will the electrons have anywhere to move to? No. So if they don't have anywhere to move to, you don't have current. So it's just going to sit there stationary. You have to complete it to a circuit. But even if you connect it to your meter, is your meter a load? So if you connect your meter, you just completed the circuit, now you're going to measure. Now the electrons have a place to shake back and forth to. You've completed the circuit. The two halves of the cycle are called alternations. Alternations. Two complete alternations make up a cycle. One cycle per second is called the hertz. Hertz also has the rental car company. Spokesperson used to be O.J. Simpson. Remember that? How many of you remember that commercial? Right? OJ's like running through the airport to go get his car. Right? Police chasing him. The Hertz we're talking about here has nothing to do with the car rental company Hertz. The Hertz we're talking about here was Heinrich Hertz. Heinrich Hertz. We used to actually call this cycles per second. If you find any, I don't know what the cutoff date was on that, but if you find any older radios, it'll say cycles per second. Cairo 710, 710,000 cycles per second. We now call that 710,000 kilohertz. We named it after Heinrich Hertz. I think Heinrich, we had a problem calling it Hertz because of Heinrich's political affiliations in the late 1930s. I think eventually science got caught up with that, and let's give Heine the credit he deserves. And the rest, of course, is history. We see here these cycle, and remember these degrees here are associated with the degrees of rotation of the armature through the magnetic field. It's that simple, it really is. When you rotate it 180 degrees through, you go from 0 to a maximum of 90, now you're back to 0. So you've put it under the influence, the strongest influence in this first 180 degrees of the magnetic field. Then on the back side, you're putting it under a negative influence of that same magnetic field. You're cutting the lines of flux. Remember Lenz's law? Left-hand rule. What kind of a wave is this? Sine wave. Okay? Sine wave. What is the sine? How many of you got your scientific calculators handy? Break out your scientific calculators. What is the sine of 180 degrees? How can that be? 0. How can that be? Does that make sense? 180 degrees, the sine is 0? What's a sine wave doing at 180 degrees? It's at 0. So your calculator just proved it. Let's try something extreme, like what is the sine of 90? What is the sine of 90 degrees? 1 what? 100%. 100%. The sine of 90 is 1. So it means 100%. What is the sine of, I'm thinking of a number between 90 and 180. 220, no. 120. What's the sine of 120? 0.866, so 86.66% of 100 occurs at 120 degrees. Check this one out. You want to do something really funky? Right? What is the sine of 270 degrees? -1. The calculator knows that we're operating during the negative alternation. If you plug in 270, it knows that it's the negative alternation. So for a lot of you that never had any use for trigonometric values on your calculator, check that out. Now you got that sine key. You could predict what is known as the instantaneous voltage present at any point of a sinusoidal waveform. Isn't that the bomb? I could say, what voltage is present at 337 degrees? You could plug in sine of 337 and that gives you the percentage. You're obviously going to have to know what this peak value is. Peak multiplied by the sine of that value will give you the multiplier. Did any of you realize this prior to this lecture? Kind of cool, ain't it? Sine key in the calculator, you could predict any voltage present along and what exactly is going to be present as what's called a instantaneous voltage. Meaning what we're doing is a sine wave, we're stopping it at a specific instant and saying what voltage is present. Okay? Remember that. That's a powerful tool for you. And by doing that, you're doing like that there trigonometry. But shh, keep it a secret. Armature is the rotating loop of wire sinusoidal waveform, also called the sine wave. But if you want to impress your wife, your neighbor's wife, your best girlfriend, what were you studying in school tonight? Huh. My professor was lecturing on the attributes of the sinusoidal waveform. Makes you sound like you're paying a lot for tuition. Can be produced by mechanical and electronic means. Mechanical means rotate the shaft. How we rotate the shaft, it's up to you. Electronic methods mean we're going to have an electronic circuit called a function generator. It's what we use in the lab next door to create different AC signals. And it's a circuit that makes that sine wave. But the purest way of doing it is really with a generator, rotating a shaft. There's also another way, too. Some of you in mobile electronics may be familiar with it. There's something in your car that you can plug an AC device into and give you AC. And your car, of course, is a DC system, low voltage system. It's called an inverter. Very good. Any of you heard of an inverter? Any of you own an inverter? Any of you own 2 inverters? 3? Anyone here own any big ass inverters, like a 5,000 watt inverter? I had one for a while. Bought it on the used market. I sold it to a guy. I actually wanted to live off the grid. I'm like, what am I going to do with this thing? I got a backup generator at home. I wasn't going to put in a solar system or anything. But I got a nice backup generator, started power my whole house, got it wired directly in and stuff. But then, man, my buddy dropped a bomb on me about a couple months ago. He's a pilot, and he knows that I love aviation and stuff. It's like, Joe, I can't believe, like, out of all the people I know, you don't have, like, an APU powering your house in a power outage. And I'm like, why didn't I think of that? APU is an auxiliary power unit. It's a small jet engine. Like, for an airplane that's parked, they'll run that to power all the electrical systems. So, I mean, that would be the deal, living next to me, man. The power goes out. How long are we going to be listening to that? until the power comes back. And you'd get that kerosene smell and everything, man. Wouldn't that be the... I think I'm going to do that this summer, head down a freaking desert and go to pick apart the aviation, pick apart and get myself a good APU. The only problem with the aviation APUs is they produce 400 hertz. They produce 400 hertz. They don't produce 60 hertz. Aviation uses 400 hertz systems.
Why so high?
Precision. The old navigation systems needed cleaner power. And on board aircraft specifically, they have what's known as an inertial navigation system. And what that would do is take track of every motion the aircraft made, and it would keep track of all of that in the computer, so that an airplane could take off from Seattle and then fly to Hawaii with really no external navigation aids. They still would use external navigation aids to check their plot and everything, but the inertial navigation system should be able to get under. My submarine had an inertial navigation system. And a submarine, I know some of you may find this shocking, doesn't have windows. So literally, when you go underwater, you keep track of how deep you dive, every time you turn right, every time you turn left, every time you slow up, and that inertial navigation system is keeping track of that. This is kind of like, you know, we all get up in the middle of the night to take care of business, right? I'm not talking monkey business, I'm talking business, right? So how many of us turn the lights on to go take care of our business? How many of us could find our way to the bathroom in the dark? Okay? That's because your mind has an internal inertial navigation system. You know when you get out of bed, you know, and how many paces over, and then, you know, you turn right, and then the doorknob, and, you know, you can find the bathroom in the dark. Yeah, oh, jeez, who put that there, you know? Happened to my wife the other morning. She gets her up early a lot, and I don't know, she hit something, and oh! Jeez, what the heck's going on? But that's an inertial navigation system. It's really important for a submarine with nuclear weapons to know, because basically underwater, you're making all of those maneuvers, right? And then what you got to do is be able to pop up and then launch a nuclear weapon and have it hit its target. And if you didn't know where it was, maybe you're going to launch it in the wrong direction or whatever. So it was very, very important. So by using a 400 hertz system gave you cleaner power, which got better performance out of the inertial navigation system. So aircraft would use the same technology. Identical to the trigonometric sine function. I already let the cat out of the bag with that. You all could do it. The sine of, plug in the degrees. The key is you got to make sure your calculator is in the degree mode. If your calculator is not in the degree mode, don't ask me how you got out of the degree mode. That is normally the default for the calculator, but by hitting the wrong sequence of buttons. The bottom line is if you are not, because you could be in the radian mode or the gradient mode, that's not going to work. For sine function to work properly, you have to be in the degree mode. So hopefully you paid attention when we were during this lecture and you were getting the same numbers as everybody else was getting. If not, you may have to look up Google, data sheet, instruction manual on your model calculator, and that'll show you how to change modes and make sure you're in the degree mode. AC values, each point on a sine wave has two numbers associated with it. The degree of rotation, this is the angle to which the armature has turned, and the amplitude, the maximum departure of the value of an alternating current or wave from the average value. Peak value is the absolute value of the point on the waveform with the greatest amplitude. So what we're looking at right here, this is the positive peak, this is the negative peak. So this right here, check this out, and this is another one that I've seen on professional exams. Over the period of a cycle, what is the average voltage of an AC sine wave? Thank you. Smart people, that said 0. Because over the average, this counters this out, and you end up with 0. This here is like this is my freaking finances. Okay? I make the money, I spend the money. Okay? And in the end, there's literally nothing left over. I was just paying my American Express bill this month, and literally there's like $3 It's kind of funny. I work, they give me, Lake Washington gives me money. I give the money and hand it directly over to American Express. You know, no middleman. No middleman. Actually, there is a middleman. It's called Bank of America. All they do is they take it and then they distribute it. And there's supposed to be a mortgage somewhere in there. That's ironic. So that's what they're talking about here. So the maximum departure from 0 is the peak. The maximum negative departure from 0 would be your negative peak. Peak to peak value, well, that's the maximum departure between your positive peak and your negative peak. And the thing of it is, the reason that we're teaching this to you, the reason we're presenting this to you, is different tech manuals, different pieces of equipment may reference some of these critical attributes. For some applications, they just may want to know what the peak voltage is. For other applications, they might want to know what the peak-to-peak value is. So it really doesn't matter. You know, I mean, I'm a pretty quick study. If I'm driving 55 miles an hour on I-5 in Bellingham, you know, 55 miles an hour, I'm driving probably at or below the posted speed limit. Okay? I go into Canada and I'm driving 55 miles an hour. Well, Canada don't roll that way. Okay? It's kilometers per hour up there. So it's kind of the same thing. Whether I want to call this 12 volts peak or 24 volts peak to peak, it depends on the application. It could be both. Well, yeah, but it's 24 volts peak to peak. Well, yeah, you're right. But the manufacturer doesn't think that's important. They just want you to ensure that you're getting 12 volts positive peak out of this. Okay. Make sense? So you just got to be able to recognize the differences and articulate the differences. Now, one of the big things here, effective value. This is the amount that produces the same degree of heat in a given resistance as an equal amount of direct current. Can be determined by the root mean square, RMS process, also called the RMS value. The amount that produces the same degree of heat in a given resistance as to an equal amount of direct current. This here is a blown landing light off my airplane. This is a 13 volt light, 12 volt system, and this is a 100-watt bulb. Okay? Really nice polished glass on the inside. This thing really reaches out and sees some stuff. I mean, because, you know, you're coming in on approach or whatever, and you've got to be able to see the numbers and align with the center lines. You know, you've seen landing lights on aircraft before. Even though it's 100 watts, it's a nice beam, a nice, clean, clear beam. Now, you want to modify this one? Glass? That'd be the deal. Get FAA, PMA approved. Could retire. Just sell them for an exorbitant amount of money. This lamp, if I applied 12 volts DC to this lamp, it would be this bright. It'd be this bright. You understand what I'm saying? It'd be 100 watts bright, it'd be this bright. If I applied, how many volts did I apply to it? 12 or 13? 12. If I applied 12 volts, the same value of AC, RMS, or effective value, you know how bright this bulb would be? It'd be the exact same brightness. So the effective value means it will have the same effect as the equivalent amount of DC being applied to a device. So quite frankly, with a bulb like this, an incandescent bulb, that's a really good example. I'm so proud of my example. It's a really good example. This is an incandescent bulb. There's a filament inside. Whether I apply 12 volts DC to this or 12 volts AC to this, it's going to be equally as bright. As long as I apply 12 volts AC RMS or 12 volts effective to it. Does that make sense? Now the thing about RMS is RMS is actually equal to 70.7% or 0.707 times voltage peak. .707 times voltage peak. So if I'm going to apply 12 volts RMS to this, what's the voltage peak going to be? Let me show you a little trick. You see this .707? This is a number you got to remember. It's not remember as in memorize, it's a number you got to know. Plug this in your calculator, .707, and then on your calculator you've got a key that's 1 over x. It's called your reciprocal key, or x minus 1 on some of yours. What is the reciprocal of .707? 1.414. Make sure you use that whole number. Don't round that number off. So it's 1.414. Okay? What's 12 volts times 1.414? 16.9 volts peak. If I apply 16.9 volts peak voltage to this, it's going to be this bright. If I apply 12 volts AC RMS to it, it's going to be this bright. If I apply 12 volts DC to it, it's going to be this bright. Have I moved? It's the same. What's that number, 16 point?
97.
Multiply that times 2.
33.9.
If I apply 33.9 volts peak to this bulb, it's going to be this bright. See, they're all the same, but they're all different values. Does that make sense? So the key is understanding what you're being given in a technical document and why they're referencing that. That's one of the classic things in audio that used to crack me up. 1,000 watts peak. Well, the thing basically is a resistive load. So basically, RMS is going to have the real effect on power, but some marketing dude attended Joe Grenick's class and like, wow, peak, sounds more powerful. We'll put that in our marketing literature and, sell it. 1,000 watts peak, 1,000 watts peak output. Using CMOS technology. CMOS since 1972, CMOS. But it sounds cool. Marketing, you got to be careful with numbers because they all say, right, the bulb, it's all the same number. So that's a trick on how to get that .707 and then make that the multiplier. So if you're at effective and you want to make the number peak, you got to multiply it by a number larger than itself, 1.414. If you're at peak and you want to make it RMS, you take 70.7% of that value and that gives you peak. Period is the time required to complete one cycle of a sine wave. We're all familiar with different things in life that have period cycles, right? The tide. There's 2 high tides a day, there's 2 low tides a day. If any of you are into fishing or boating or anything like that. And it was kind of funny, I'm ex-Navy, but I never understood it. It's like, we're on a nuclear submarine, man. I mean, can't we just plow through the freaking tide? Why do we have to be up at 2 o'clock in the morning to leave with the tide? It just never made sense to me. But you have to do that so you don't hit rocks, submerged rocks, when you're pulling out of port and stuff. So the tide has cycles to it. The moon has cycles to it. The earth has a cycle, a rotation, 24 hours. In electronics, the period that we're talking about is always going to be measured in seconds. The letter T is used to represent period. So T equals means I want an answer in seconds, unless I specify otherwise. Frequency is the number of cycles that occur in a specific period of time. It's expressed in terms of cycles per second. Unit of frequency is called the Hertz, named after Heinrich Hertz. 1 Hertz equals 1 cycle per second. So if you find any old radio gear, it may say cycles per second. World War II era radio gear, if you go and get a tour of a B-29 bomber, B-17 down at Boeing Field, you'd look at it and you'd see the radio gear and it would say cycles per second. Let me go back to that real quick. There's an easy way to switch between the two. If you know the frequency, take the reciprocal of the frequency and that will give you the period. How many times does this fit into 1 second? Also, by algebraic manipulation, F, measured in hertz, is equal to 1 over time. So, what comes out of our wall here as far as frequency? 60 hertz, okay? Plug this in the formula right there. 1 divided by 60, what do you come up with?
Is it 0.016666?
Give it to me in proper terms, please. It's how I roll. It's kind of my thing.
16.6 milliseconds.
16.67 milliseconds. A sine wave that comes out of the wall repeats itself every 16.67 milliseconds. Okay, so what that looks like would be this. Every 16.67 milliseconds repeats itself. 16.67 milliseconds repeats itself. That means that we could cram 60 of these cycles in 1 second. 60 cycles per second. 60 hertz. 60 cycles per second. 60 hertz, synonymous, same thing.
So if you divide that by 2, which gives you about 8.3 milliseconds, that means that the lights are turning on and off every 8.3 milliseconds, right? When it goes from the positive to the negative, technically, but we just can't pick it up.
And in Europe, it's 50 hertz, so that period of time is even more pronounced. But for an incandescent bulb, the filament doesn't cool down enough to, for some of these bulbs, you will notice,
A little flickering.
and some people, they don't dig it. Some people don't dig it. There's a lot of studies. It's a whole separate area of study. To be honest with you, lighting and what power are you using? Do you have to condition the power? You want to apply DC, convert the AC into DC, you know, so you get the right mood, set the right mood. You have a graduate out of the program that he works in aerospace, aircraft interior, exterior lighting. And he has sent me pictures and emails from around the world. He'll be sitting on an Indian Air 767 over in Mumbai with a light meter measuring the frequency and the light and making sure it meets the customer's requirements. Because all airplanes that Boeing makes are not created equal. Different cultures have different requirements for lighting and effect and mood, and different airlines. I mean, they want people to put them to sleep, and you know, I don't know if you've ever flown. You know, like it's funny. You fly on a domestic flight, and you know, people leave the windows open. You know, not the windows open, but you know, the shades up. And you know, during the day, if you're on an international flight or whatever, people close them because again, it's dark and it's easier to sleep. You don't see the sun, and it creates a different effect. So the same thing could be said for lighting. It creates different effects, and there's people that study this stuff and spec it out. So like, yeah, we want to keep our, you know, our passengers like calm. We don't want them to be all riled up, and they'll sell them a package for lighting, and big deal.
Years ago, has to do with single phase, 2-phase, 3-phase in wood shops and table saws, was that the saw blade would act as if it was standing still, like it was not even in motion because of the reaction with the lighting. So they change, and you could literally go to make an adjustment.
Strobe effect, yeah.
And it would make the blade look standing still. And there was lots of accidents that happened, and so they changed lighting to 2-phase. Yeah. Apparently there was a big problem about the old people that worked in the wood fabrication industry many years ago.
Does make a difference. So make sure you know how to perform those calculations, and it's easy. Once you measure this, you're going to measure this on the oscilloscope. Once you do that, it's easy converting it over to frequency. Non-sinusoidal waveforms are generated by specifically designed electronic circuits. They're used to represent either current or voltage. This is known as a square wave. The thing I want you to remember about a square wave is half the time it's on, half the time it's off. Okay? And it looks square, literally half of it's on, half of it's off. On and off, on and off, on and off, square wave. And also be able to articulate what this is. This is holding a constant amplitude for a period of time, and then it immediately drops, almost instantaneously drops, and then holds that off condition, and then instantaneously rises. This is a triangular waveform. A triangular waveform has a rise time and a fall time that are linear and equal. You understand what I mean by linear? Straight line is linear. Curve is not linear. Curve is nonlinear. That's why it's called a curve. So a rise time and a fall time that are linear and equal. If you describe that to me as a tech assist, I'm looking at a waveform that is linear and the rise time and fall time are equal, I'd say, bingo, you're looking at a triangular wave. How would you articulate this? How would you describe this to me over a satellite phone? You're trying to fix something and you're looking at a wave pattern that you'd never seen before. Bzz. Linear is a straight line. So I have a long linear rise time and a relatively short linear fall time. I'd say, oh my golly, you're looking at a sawtooth waveform. And to be honest with you, what a sawtooth waveform is used for is actually developing like a raster scan on a CRT monitor. It's what actually drags the electron beam across the screen. This increasing voltage is dragging the beam left to right across your screen. And then drastically, it's resetting it back to the left side of the screen so the naked eye can't even perceive it, and then it paints the next line, pow, the next line, pow, the next line, on and on and on. That's how a sawtooth generator works. Sawtooth generator works, that's because you got a dot in the middle of your screen. You turn your TV on, you got a dot in the screen. That sawtooth generator probably has failed. Same thing with your oscilloscope. That's how an oscilloscope works. When you get a display up, basically what that display is that beam getting pulled left to right across the face of the oscilloscope. It's a sawtooth generator that's creating that. Low voltage to a high voltage, and then rapidly resetting it faster than the naked eye could perceive it. Square waveform useful as an electronic signal because its characteristics are easily changed. Triangular waveform used primarily as an electronic signal. Signal is, you know, when I use this, I use the term signal loosely. I use the term signal loosely. Actually, I don't. I probably hear more so than anybody use it accurately. Signal means intelligence is behind it. Signal means intelligence is behind it. It's what my job classification in the military used to be. Signal intelligence. ELEC, electronic intelligence. SIGINT, signal intelligence. And first of all, if you have a signal, it means intelligence is behind it. If you saw the movie Contact with Jodie Foster, that's what she was looking for. She's out there down in freaking New Mexico with those big dishes. Been down there. It's a phenomenal place. Magical. Like over a mile above sea level, and you're out there in the plains, and it's just lighting up a stogie, and it's magical. Out there at night, whole nother ball of wax, man. There's stuff out there flying around at night. Jodie Foster was looking for a signal in outer space. If she found a signal in outer space, that basically would signify that she found intelligence, extraterrestrial intelligence, because signals just don't occur randomly in nature. Signal means something is behind it, so that's what she was looking for. And if you saw the movie, hey, she found it, I think. She either found it or she got a hold of some magic mushrooms. I still haven't figured it out. She went to Puerto Rico and then thought she was on another Fluorescent planet. Maybe she wasn't in Puerto Rico. Maybe she went on the flight to Amsterdam. I've been on that flight before, if you know what I mean. I don't even know what I mean. Don't even know what I mean. Wasn't scary until you shut the lights off and you could still see everything real clear. I don't even know what that means. Sawtooth waveform used to sweep the electron beam across the screen, creating an image such as in television sets, radar displays, any of those cathode ray tubes. Fundamental frequency is a frequency that represents the repetition rate of the waveform. This here would be the fundamental frequency for a 60 hertz waveform. Fundamental frequency. This is the period, right? 16.67 milliseconds. Reciprocal of that gives me frequency, 60 hertz, fundamental frequency. Harmonics are higher frequency sine waves that are exact multiples of the fundamental frequency. Odd harmonics are going to be odd multiples of the fundamental frequency. Even harmonics are going to be even multiples of the fundamental frequency. So this means whenever you create a frequency, a signal, you're going to create these harmonics after it. Can't be avoided. It could be mitigated, but it can't be avoided necessarily. Now, since these harmonics are all out there just waiting to be utilized, square waves are actually made in an electronic circuit by taking the fundamental frequency and all the odd harmonics and adding them up. When you do that algebraically, you end up with a square wave. If I put a square wave on a piece of test equipment called a spectrum analyzer, you would see that fundamental frequency and then you'd see all of those harmonics lined up in lower amplitude, but they'd still be present. You'd see them. Someday in the lab we'll do that. I'll call you all over. I'll say, hey, look at this here spectrum analyzer. I'm looking at a square wave, and look at them, they're harmonics. And then you'll say, oh, I remember that. 17th of May, 2011. Joe Grenick talked about these harmonics. Now I'm seeing them. My life is so much better now.
So do the harmonics have the same shape as whatever the waveform
Yep.
is, just less of an amplitude?
Less of an amplitude, but yeah, the same shape. It's just the same frequency. Triangular waveform is made of the fundamental frequency and all odd harmonics 180 degrees out of phase. Fundamental frequency and all odd harmonics 180 out of phase. Sawtooth waveforms composed of odd and even harmonics, with the even harmonics 180 degrees out of phase with the odd harmonics. The big thing about harmonics, let me just say one more thing on harmonics. Harmonics used to frustrate the dickens out of me. Earlier I was talking about my surveillance equipment, manual controlled. I hate to say it, but I was really good. I was trained very, very well. I was really good at what I did. Then, this computer operated system. Well, a computer is only as good as how it's programmed. So one of the problems that we had, it was kind of funny, because I could laugh at myself. I was very, very junior, and it was on my first mission in the Mediterranean. And we used to go to what were known as Soviet anchorages. And the Soviets, because they didn't have any warm water ports, they were in cahoots basically with Muammar Gaddafi. And Gaddafi would let the Soviets anchor in these protected ports, and they'd put their entire fossil fuel burning fleet in these ports, and they'd position them in a warm water port, ready and able to go if they decided to push the button and start World War III, instead of coming out of Murmansk and all these cold water ports that were frozen. So my first mission, we went and we basically would creep up on this anchorage, and every day with electronics, they have to turn the electronics on and cycle them and run through and everything. And we're so close that we're not only picking up the fundamental frequency, I'm picking up all of the harmonics. So like, the first time that I went over there with a computer-controlled system, and as soon as our periscope broke the water in the morning when the Soviets were running the tests on their equipment, all of a sudden my screen is just like, just bogged down with every hit known to man, because the computer wasn't able to differentiate between the fundamental frequency and the harmonic. It just was getting wow, it's a really electronic, noisy environment out there, and I'm going to try to process everything. And that was something that I had to get my learning curve up on, is how do we mitigate this? How do we filter this? How do we attenuate this so that we could sort out the good from the bad and make this a valuable exercise, a valuable mission on gathering the intelligence. So those harmonics could be really bad news because they could lead you astray, and you needed to be able to analyze that. Actually, one of the techniques that I used to use, and maybe in the fall we'll see who teaches you the test equipment class, but one of the things, the techniques that I used to use is, in my operator position, I had a keyboard and 2 computer monitors, and I had some equipment up here. I mean, it's just loaded with equipment. Anything I wanted to do, I had gear, arms reach away to be able to analyze stuff. But one of the things that I had an oscilloscope up here set up for with a function generator is I would take, if I questioned the computer, I would take that signal and route it to the oscilloscope, an oscilloscope, just like we have here in the lab. And then what I would do is I'd get a function generator, just like what we have in the lab. And I would feed the input into the function generator, out of the function generator into the oscilloscope, into what's known as my x-axis. So my y-axis is the unknown frequency. The x-axis is my known frequency. And I could mix those 2 signals together on the face of my oscilloscope. And does anybody know what I would come up with on my oscilloscope? Here's my oscilloscope face. If I mix those 2 frequencies together, anybody want to take a guess at what I'm going to end up with? I get a circle. I'd get a circle. Because the unknown on my vertical axis matches the known on my horizontal axis, and they mix. And if I got something that looked like this, it's a harmonic. If I'm at the perfect frequency, it's going to be a circle. If I'm at double that frequency, it's going to give me one of these things. So I could get all these different patterns on the oscilloscope, but for me, I had the equipment set up like that so that randomly I could, if I was looking at something, because I had to act really quick on analyzing stuff. Very, very quick. I mean, we had literally a matter of seconds to, is this a safe environment for us even to be near the surface? Or is somebody looking out there looking for a periscope that's going to target us, boom, send a sub-rock down and blow us to kingdom come. So I had to make a quick decision. Is it a threat or not? And by having that connected like that, and I look at the computer and then pow, immediately patch it up to the oscilloscope. Look, circle. Yeah, the computer's not lying to me. Or, no, I'm getting one of these. The computer's lying to me. This isn't even the freaking frequency that we're at. It's lying to me. I could discount that and then move on. It's called a lysojoule pattern on the oscilloscope. And I'll show you in the lab someday on how to do that. It's kind of cool. It's kind of cool. In summary, AC is the most commonly used type of electricity. So AC comes in 2 flavors. Power, to power cities, communities, buildings. Power, and signals. And signals basically is anything that has intelligence behind it from DC to daylight. Cycle is that amount of time which it takes for a waveform to repeat itself. Alternations, an AC sine wave has 2. One positive, one negative. Hertz, rental car company, O.J. Simpson used to represent. Sinusoidal waveform or sine wave could be used, is actually the most common form of power distribution. Peak value of the sine wave is the maximum deviation from average. Effective value of AC has the exact same effect as if you apply DC to a purely resistive load, like an incandescent lamp. How to determine effective value by the RMS process? It's simple, 70.7% of peak. I also showed you the technique on how to get the multiplier to go from peak RMS to peak. Period, measured in time, frequency measured in F, and the relationship F is equal to 1 over T. We also talked about non-sinusoidal waveforms and where they come from. It's the kind of stuff I used to read to my kids when they were growing up. Tonight, we're going to read about non-sinusoidal waveforms and where they come from. In the beginning, there was what was known as the fundamental frequency. Tomorrow night, we're going to talk about Adolf Hitler and what he tried to do. Yeah, my wife, man, she'd run me out of there. Forget it, I'll read to the kids. All right? You wanted me to read to them, these are my books. It's the stuff it's how I roll, man. Square waves, triangular waves, and sawtooth waves. All of these waveforms represent intelligence, and all of these are made up of harmonics, fundamental frequencies and harmonics added together. And that's how we create those things. That's how a function generator works. Internally, it adds all of that stuff up and then gives us the circuit, the signal that we want. Any questions? Everett, hit me.
I was just wondering, do you have any idea why 60 cycles?
No, it was actually, that's a good question. I can't answer it off the top of my head, but it was really interesting. A few years ago at the Consumer Electronics Show, there was a display that was set up of all these worldwide adapters, okay? And there are some places that have some really goofy plugs and goofy voltages. Well, and actually Japan is interesting because they're 120 volts like us, 115, 120, but it's 50 hertz. 50 hertz? Yeah. So stuff like your electric shaver will work. It's just going to work a little bit slower, but it'll still work. But anyway, this guy that was the sales rep for the company, he used to be a history teacher. And it sounds like he got his job because he knew the history of all of this stuff. And it all goes back to politics. Like even in the Caribbean. I love the Caribbean. It's my favorite place in the whole freaking world, okay? The Lesser Antilles, right? The Outer Antilles, beautiful, beautiful area. But it's funny. My favorite place in the world of all places is St. Martin. Half Dutch, small island, okay? Smaller than Tacoma, small island, half Dutch, half French. And they've lived harmoniously for hundreds of years. On the Dutch side, it's pretty much US-style plugs. On the French side, no. And it's a small island. And it's all because of history and who ruled what and where the lines were drawn, and that really is the governing factor. Specifically, why 60 here, why 50 there, I don't know. That'd make for an interesting, I guess, research project. But a lot of it all played politics. Politics was behind most of those decisions. They want to be different. 400 hertz, specifically for industrial applications and aviation, it was for the accuracy. Because ideally, you know, if you've got 60 alternations per second, now you could cram 400 of those in there. When you go to clean that up and convert that from AC into DC, you're going to end up with much purer form of DC. So that's why they do it.
The ripple will be closer together.
Absolutely. It'll be just about null. That was one of the, I actually had a friend that I served with in the military, and he went to go to work for Berkeley Lab. They have a particle accelerator down there. And I went down there, hung out in Berkeley for a while. I know, if you know what I mean. I don't even know what I mean. We did some crazy stuff down there. Really, the San Francisco Bay Area is a hoot. So anyway, he gave me a tour of their particle accelerator, and it was interesting what they were doing. Is they're buying energy from the power company, and then literally what they would do is they would turn a giant motor, and the motor would turn their own generator, and what they were generating was 12-phase power at a higher frequency, and what they would do with that is ultimately convert that into pure DC to power this particle accelerator. And I mean, the power supply was a cage, and it had interlocks, so like you could walk into the power supply, and it's like they had these big, huge rectifier tubes, and it's fascinating. I wish I had pictures. Wish I had pictures, not from the entire weekend, but just from that part of it.
How do they determine the
hertz, you know, say you have 60 hertz and the power company all of a sudden wanted to change to 100 hertz, what?
No, they aren't going to do that.
Well, I mean, I know, but to change, what sets, I guess, the hertz?
Kind of back to Everett's question. It's really government. It's political. It's the same thing even with us, Canada, Mexico. You know, we've got interties. We're sharing electricity back and forth, you know. Canadians want to be that freaking different, right? Why don't you guys change like different hertz rate and then like, actually I think we're probably buying electricity from them. They got those gas reserves and all that stuff up there. I mean, that's like freaking big time. That's big time. I drove the Alcan last summer. I had friends that moved up there and I was just kidding around. Hey, you want somebody to ride shotgun? It's like, you'd be willing to do that? It's like, we don't want you to ride shotgun. We got an extra vehicle that needs to be driven. You want to go up with us in convoy? Yeah, why not? So I drove the Alcan, phenomenal. And that whole area up in northern BC where all the oil exploration, we paid more per gallon of gas or liter of gas up there. Our hotel costs more, food costs more, everything because of all the oil and gas exploration taking place up there in Canada right now. So they could probably kick our butt with natural resources, you know, at this point. Our conventional means, but it's political. We're friends with them, stick with 60 hertz back and forth. We have an intertie with Mexico. Sell them our electricity. If they were on a different standard, then that'd be a bit of a hassle. The only exception to that is actually down at the Dalles on the Columbia River. They have a direct line. This, I shouldn't tell you about this. It's too late in the night to tell you about this. Bonneville Power Administration has a direct tie with the city of Los Angeles, and it starts in the Dalles. If we hopped in my airplane and we flew down there, Columbia River, got there, followed those power lines, we'd end up in a place called Los Angeles. And you know what they're doing? They're generating AC at the dam. They're converting it into DC, and they're shipping DC to LA. Supposedly, I've asked Bonneville Power when they've been in here that exact same question. And supposedly, they're getting higher efficiency out of converting it into DC. Once it gets down to LA, what's the first thing they got to do with it? Convert it back to AC so they could, you know, power the valley.
I thought that's why Edison failed, was because DC didn't transfer.
It'd be a great thing to study. It'd be a great thing to study. We could, you know, we have friends at Bonneville Power, get them in here as a guest speaker. We could actually plan a field trip, a class trip, open. It's one of the things that y'all students, I'm going to rail on y'all students here for a second, right? As college students, you could get yourself into places that the general public cannot get. And I will help you get into those places because I, as a teacher, could get into places that the general public can't get. One of the great tours that we did years ago, I haven't been back since, is the power generating plant, Snoqualmie Falls. Not the one downstream, the one underneath the freaking falls, behind the falls. It's like the Bat Cave. I mean, I'm hanging out there. I expect like Batman, you know, Robin like looming in the shadows wearing tights. It's the real deal. We got there as students. It's not open to the general public. We scheduled it ahead of time. We all had hard hats. We all rode the elevator down in. If you've been to Snoqualmie Falls before, that output, if you're looking at the falls, there's like this cave and water coming out of it and stuff. We were down there. We're standing there looking up at the falls like, this is a freaking hoot. Want to do stuff like that, you know? You could do that as projects. We haven't been on tours in like eons because it's a pain. I mean, it really is. We could do that kind of stuff. Go down to Columbia River Gorge. I mean, charter a freaking bus, do some fundraising, get a freaking bus or kick in or whatever, motor coach, go down there, get a tour. See that. I mean, you're actually converting it to DC in this giant room. And you mean that DC, that wire's connected to the city of Los Angeles? That's cool stuff. I mean, you watch stuff like that on Discovery Channel, you could see stuff like that with your own eyes. And this is the leverage that you could do, because everybody loves helping out college students.
I was working with some old timers at PSC, and they were telling me the cool thing about that power plant at Snoqualmie was when they built it, they only had the one elevator shaft that went down. So he was saying that anything and everything you see down there was deconstructed up top, brought down the elevator shaft, and then reconstructed down below. Is that true?
From what I understand, yeah, that's how they had to do it. And that was all, too, the neat thing about being down there, that was all the late 1800s when that was built.
Yeah.
Carved out by hand. I mean, just phenomenal. Anyway, hey, we're handing out a take-home